Okay, I can do a quick introduction. So Qiming, he's a PhD student at the University of Auckland, and he works on reasoning over natural language and in general in neurosymbolic AI. And he was recently in London to present this paper that he also will present now at the Joint Conference of Learning and Reasoning. And so, Qiming, when you're ready, you can start.
Okay, thanks, Christina. Yeah, so good morning, everyone. So this is Qiming Bao. I'm from University of Auckland, New Zealand. So basically, I'm a PhD student, and my supervisor is Michael Whitbrew. So this paper is just accepted by the IJCLR-NeSy 2022. So the title of this work is Multi-Step Deductive Reasoning over Natural Language, Empirical Study on Out-of-Distribution Generalization. So, okay. So let's first introduce our labs. So basically, the Strong AI Lab is led by Professor Michael Whitbrew at the intersection of machine learning, reasoning, and natural language understanding, with the additional focus on achieving the best social and civilization impacts of increasingly powerful AI. And the LIU AI Lab is led by Dr. Jiameng Liu. We are on the AI research group at the University of Auckland. So we are engaging in artificial intelligence research and development from both the industrial and academic sides. And our research interests cover a wide range of topics across the modern AI world, including deep learning, reinforcement learning, multi-agent system, natural language processing, and complex network analysis. So first, let's introduce the basic concept for the symbolic logic programs. So symbolic logic program basically can express the logic statements and expressions in symbols and variables instead of natural language. So here's an example of logic programs expressed in Prolog. So in this case, we have one rule and one constant. So this rule basically means, so if Qx, so given Qx, and then we have Px. So in this case, the uppercase x is the variable, and the lowercase is the constant. So, and then we have some more symbolic logic programs example. So first of all, let's look at the left-hand side, which is the fact. So in this case, given the EL, this constant, so the question mark EL is the question. So 1 means true, so 0 means false. In this case, we can exactly find the EL is funding from the context. So in this case, EL is true, and the ID is false. And then we have unification. So in this case, we have O double V. So in this case, we need to make sure the double V are matched at the same time. So we look at the question. In this case, we have O double D. So we can see the double D can exactly match to the double V. But the next question cannot do the exactly match, so it's false. And then we look at the one-step reasoning. So in this case, one step means we use only one rule to derive the answer. So we can see the question. So question is PA, so whether PA is true or false. So we can use the context information. So given QA, which is a constant, and then use the rule. So if QA is valid, and then we have PA. So in this case, we can use this rule once to derive PA is true. And then we can say that PB is not found from the context. So we can say PB is 0, which is false. So it's under the closed word assumption. If we cannot find the support information, and then it's false. Oh, sorry. So then let's look at the natural language reasoning. So in natural language reasoning, logic statements are expressed in natural language instead of symbols. So we have the semantics of logic, such as propositional logic and first-order logic. And then in natural language reasoning, we have the diversity and flexibility of natural language, such as polysemy, a paraphrase of sentences. And then we look at the reasoning part. So reasoning basically obtain unknown information based on the existing information. And we have basically the 3 types of reasoning. So deductive reasoning, inductive reasoning, and abductive reasoning. So deductive reasoning basically is given the premise and rules, we can use this given information to derive the conclusion. And inductive reasoning is given premise and conclusion to derive the rules. And abductive reasoning is given rules and conclusion to derive the premise. So abductive reasoning can be seen like to explain the how to process the answer. And we have more example from the reference here. So basically we publish another paper called the Abduction Rules, which is focused on the abductive reasoning. And we contribute a new abductive reasoning data set. So this paper is accepted by the funding of ACL 2022. So then let's look at in detail about the example for natural language reasoning. So in this paper, we look at the example like this. So we have the input facts, input rules. So those information are the context information. And then we have several questions. So like the Bob is green. So those are the questions. And then we need to derive whether it's true or false. So let's look at the first question. The first question is Bob is green. So how to derive the question, so whether it's true or false. So we can use the information given from the context. So for example, we have Bob is big. And then we have use a rule, big people are rough. So we can derive Bob is rough. And then we have another rule called all rough people are green. So we can use this rule to derive Bob is green. So in this case, we use the rules twice to derive the answer, which is Bob is green. So we can say Bob is green is true. And then let's look at another example. So in this case, the question said Bob is kind. So is it true or false? So let's look at, so is there any related information for Bob? So for like the Bob is kind is true or false? So first let's look at the facts information. So there's no fact that Bob is kind. And then let's look at the rules. So is there any rules that we can use to derive Bob is kind? So we find there's a rule called if someone is young and broad, then they are kind. So, and then we can see, does Bob young or wrong? So let's look at, we only find Bob is blonde, but Bob is young is not found. So in this case, Bob is young is false. and Bob is wrong is true. So we cannot use, so based on the closed word assumption, we cannot use the information to derive Bob is kind. So basically the information is not enough. So we can only say Bob is kind is false. And let's look at the third question. The third question is asked, Dave is blue is true or false? So we can see, is there any information from facts that Dave is blue is true or false? We find there's no information that Dave is blue is given from facts. So in this case, we need to find, is there any information from rules that Dave is blue? So we can look at this rule. So this rule said if someone is broad and big, then they are blue. So we can see that is there any information for Dave around for the round and big? So we see that there's no information for Dave that Dave is round and Dave is big. So in this case, we can only see that Dave is blue is false. So, and then let's look at the research gap, which is the main research question for this paper. So for the existing models, including the deep logic and other recurrent neural network-based baseline models, so they have room for improvement in their reasoning ability over natural language. And we find existing models are not good at out-of-distribution, OOD generalization. So in 3 scenarios. So first is when model is trained on data with shallow reasoning depths and test on the data with deeper reasoning depths. The second one is when the model is trained on the synthetic generation data and test on the data paraphrased by human. And the third one is when model is trained on unshuffled data and test on shuffled data. And then we find exist multiple step deductive reasoning data set like the pair rule and concept rule version 1 and version 2. So for those data sets, they have unbalanced distribution over the reasoning depths. So that means only a small portion of data set require deep reasoning. So deep reasoning basically is the depths between 2 to 5. So here's the model overview. So the model architecture is based on the deep logic model. And basically we have 2 modifications. So first is we use the word level embedding to make the model to represent the natural language and understanding natural language. And second is we use the data attention, which is a new model borrowed from the dynamic memory network class, which actually use the data attention to perform the 100% test accuracy on the baby deductive reasoning task. So that's why we borrow this architecture in our model. So I will describe the model in detail in the later slides. So firstly, let's look at the word level embedding. So in this case, we need to use, because we need to process the natural language question, so we need to use word embedding to do that. So the input to the network consists of context and statement. Basically, it's the context and the question. So statement is the question. So the input sequence is represented. So we use glove word embedding to represent the input sequence. And then we concatenate the representation of context and statement, and then feed to the gate recurring unit, which is GRU. And then we look at the iteration part. So the iteration process is from the deep logic. And the iteration step consists of attending the rules. So we compute a new state using each rule and the old state. To apply a rule, we use another recurrent neural network called the inner GRU unify. So this module is processed every iterable of given rule. So the inner GRU unify needs to learn the unification between variable and constants. So this module is basically can see as a neural unification module. And also we need to use this model to learn how each rule interact with the current state. So here's the gate attention. So gate attention basically is the first proposed by the dynamic memory network class, basically which is achieved the 100% test accuracy by using gate attention on baby deductive reasoning task 15. So that's why which gives us the idea of integrating gate attention into deep logic. And also GRU can use gate attention to update the internal state. And here's the established baselines. So we have the recurrent neural network baseline and the pre-trained language model baseline. So in this case, we have the three baseline. So here's the recurrent neural network baseline. We have the long shortened memory LSTM, which is also the baseline method on baby data set. And we also have the dynamic memory network. So which is one of the first paper used attention in the memory network. And the memory attention control networks, which is a classic method for memory network. So here's another data set that we use in the experiment, which called the concept group and concept group version 2. So those data sets are developed by Tim Hartil, which is also a team member in our lab. So basically, the difference between the two data sets is the concept group version 2 has the depth tag. So basically, for this data set, so we have the depth information for each question. So, but in the concept group, we didn't have the depth information. And if we look at the context, so basically for those two data sets, the rules and fact are implicitly merged together. So there's no explicitly fact and rules. So we only have input context. So it actually can be seen as a multi-step deductive reasoning version of baby dataset. So because baby dataset only consider the single-step deductive reasoning. But in this case, concept group and concept version 2 consider the multiple-step deductive reasoning. And here's the dataset description. So in this case, we can see for the parallel dataset. So this is the main dataset we use in our paper, which is developed from Peter Clark in Allen AI Institute. So for this dataset, you can see the main drawback is they have much more dataset on the depth 0 and depth 1, but much less amount of dataset on the depth 2 to depth 5. And we can also see the concept version 2, full version and simplified version. So full version basically is they shuffle the order of rule and fact. The simplified version, they just keep the same order of fact and rules. So you can see actually for those data sets, they have no data set on the depths equal to 4 and 5. So in this case, we find the exist multi-step deductive reasoning data set has less amount of data on the deeper depths, on the deeper reasoning depths. So that's why we have this parallel plus data set, which specifically focus on the depths from 2 to 5. So we augment the training data set from this deeper reasoning depths. So basically the idea is we hope we can build up deeper reasoning data sets to improve the model's performance on the deeper test reasoning data set. So here's the dataset description. Basically, so the entity means so basically in the dataset we have the basic structure is the subject, relationship, and object. So the entity is the basically the subject and object. So we consider different names from people and animals. And so this is basically the current different category of entity. And we have different number of relationship. So, and then we have the shuffle rule. So shuffle rule means we shuffle the order of fact and rules. So the reason that we consider this shuffle rule is we try to avoid model to be trained using the order of rule and fact. So in some case, if we keep the same order, because the dataset is synthetic dataset, so the order of fact and rules will not change. So you can see normally facts are the first and second part is the rules. So in this case, there's a situation that model will be trained to remember the order of the fact and rules. So in this case, we try to shuffle the order of fact and rules to avoid the model to memorize those unnecessarily useful information. So that's why we consider this shuffle rule dataset, a shuffle rule in the current dataset. And then we have the depth tag, which is the depth information for each question. And then we have the derivable. So derivable means the question can be derived from the context. And the NAF, which is the negation as failure. So I will show one example to explain what is negation as failure. So here's the example for negation as failure, NAF. So for this example, basically it means you can see the orange one. If someone is not wrong, then they like the cat. So in this case, we can use the negation to as the information because it's under the closed word assumption. So there's no one is wrong in this case. So in this case, someone is not wrong is true because someone is wrong is false. So someone is not wrong is true. And then we can use this information to derive the new information. So that's basically the concept for negation as failure. So actually this concept is from the logic program. So it's actually not widely used in the real world natural language. So in this case, we only consider this concept in the synthetic natural language dataset. So here's the experiment result. So basically, we use GLOF as a word vector representation to replace the original embedding for each recurrent neural network-based model. And we use parallel dataset with all depths as the training set. So basically, we put the all depths together as a training set to train the model and test them on different depths test set. So the D means the reasoning depths. So D equal to 1 means the depth equal to 1. And D equal to 2 means depth equal to 2. And then we have so NetLang. This one means the extra natural language, because we want to test whether the model has the out of generalization ability. So that's why we add the extra natural language as a test set. So in this case, we can see basically the pre-trained language model can perform a very good performance to compare the other recurrent neural network-based model. And so this one is our model, which is IMA-GLOF-G. And this one also perform better performance compared to the other recurrent neural network-based model. So the reason I put them together is so all of the above model are unpre-trained model. So they are basically trained from scratch. But the BERT large is basically we fine-tune the parallel data set based on the pre-trained language model. So that's why this probably not fair to compare in the same level. Now we still can see pre-trained language model can have a very good performance in this task, but we will find more drawback for large language model in some other cases. But here's the general case. And then we find LSTM model basically fails in this task. So basically, it means LSTM didn't learn anything about reasoning. And here is a more detailed experiment result. So in this case, we use the concept group dataset. So the simplified basically means we didn't shuffle the order of factor and roots, but the full version we shuffle the order of factor and roots. So in this case, we can see the BERT large. If we train it on the simplified version and test on the simplified version, it's actually performed very well. But if we train on the simplified version and test on the full version, it's basically like the random guess in this case. So that means the model is trained on the unshuffled dataset and test on the shuffled dataset. So it actually fails in this task. That means the large language model probably not really learn anything about reasoning. So it probably will catch some information about the location of rules and facts to help them to derive the answer. So it's not truly understand the reasoning in this case. So we also compare our model and the deep logic model. So our model actually can perform better out of distribution performance compared to the BERT large. And here's the experiment result that we want to see the generalization performance for the current model. So basically, we train on the, for example, we train on the depth equal to 1 and test on the depth equal to 1 and depth equal to 2 and depth equal to 3. So we can see the basically the so for example, we can see all of them can have very good generalization performance. So for the depth equal to 1 as a training set. And then we look at if we train on the depth equal to 3 and test on the depth equal to 1. So we can see this Roberta large can, the word drop a lot in this case. But actually we can see deep logic 1 and our model will still have a very good performance on the deep depth equal to 1. And then we also train it on the depth small equal to 1 and small equal to 2 and small equal to 3 and test on the each test set. So we can see the Roberta large model drop a lot compared to the other one. So here's the result that we fine-tune the Roberta large on different depths. So in this case, so depth small equal to 2 means we train it on the, under the depths x equal to 0, equal to 1, and equal to 2. So you can see, and we train it and test on the different depths test sets. You can see the performance on the deeper depths decrease a lot. So that means models out of distribution generalization performance is not really good. But if we train on depth small equal to 3, you can see model actually improve the performance a lot on the deeper depths. But on the actual natural language test set, it's still not really good. But if we add the actual natural language in the training set, we can see the test set for the actual natural language improve a lot. So this can be seen as a way to address the out of distribution generalization issue. Is we try to augment to do the data augmentation to address the out of distribution issue. And then we look at if we add more data set on the deeper depths, like the depth small equal to 5. So we can see the deeper depths can improve a lot. But the natural language test set, the real world natural language test set will not perform well because in this case, we didn't add the actual natural language in here. We just add the synthetic data set, but the more deeper depth training set here. So here's the result that we add our new data set called Empirical Plus into the training set. So in this case, we can see the yellow background means we add this Empirical Plus and then we perform better performance compared to the original without adding the Empirical Plus into the training set. So we can see basically the deeper depths increase a lot. But so compared to the deeper depths and the natural language test set, we can see the deeper depths improve a lot more compared to the natural language. But we can also see the performance on the natural language, actual natural language can also improve a little. Okay, I think that's all for my talk today. So thank you for your listening. So I'm also welcome to visit our lab. And also here's the QR code for the paper and the GitHub. So is there any question?
Yeah, thank you, Qiming, for your presentation. I know now it's a little bit late in Auckland, so thank you for taking the time. Is there any question for Qiming? Okay, otherwise I ask a question. So if you can go back, maybe I think it was slide 21, I believe. Yes, this one. So as you said, so we can see that Roberta does not generalize, because when you train on the simplified data set and you go to the full data set, we can see a huge drop in performance. I was wondering, so because if you train on simplified and test on simplify, and if you train on full and test on full, we can see that it works, right?
Yes.
I was wondering, do you think there is like bias in how they generate the data set, the concept rule data set, so that it kind of like the effects are always in the same order, or the rules always pick the same effects? Do you think that is the issue?
Yeah. So I think so basically the model will probably the order of the position, the order of fact and order of rules may influence the model to make decision. So basically the full version basically is the shuffle rule version. So shuffle rule, basically you can think this as a data augmentation, because during each iteration, during each epoch training, so it will have the different order of the data set. So in this case, for each iteration, it will do a data augmentation. So in this case, the shuffle rule version will basically have a more complex and more data set during the training set. So the simplified data set is quite synthetic and quite less diversity. So less diversity, if model trained on the less diversity data set, it will definitely have a low out of generalization performance. So in this case, one way is to improve the diversity of the training set, including data augmentation. So like shuffle rule is one way to do the data augmentation.
Yeah, I'm wondering if there is some other bias in the data set other than the order. Did you try to shuffle also maybe the constants names, or?
Yeah, I think it's a good idea. So in this case, we only shuffle the sentence, the order of sentences. So we didn't change the information inside the sentence. I think it can be tried to also change the order inside the sentence.
Okay, thank you.
Yeah,
any other questions? Okay, then I don't think there is any other question. So thank you, Qiming, again. And yeah, the presentation was great. And that's it, I guess. Thank you.
Yeah, thank you for your invitation.
Thanks very much.
Okay, thank you. Bye.